In this video, we're going to take a look at two more examples of L'Hopital's rule, but these examples will incorporate a slight twist. So we can see here that we have two functions, both expressed as a fraction. In part A, we're taking a limit as x goes to infinity, and in part B, we are taking a limit as x approaches 0. If we plug in infinity to the numerator and the denominator of A, we get infinity over infinity, which is one of our indeterminate forms. If we plug 0 into the second expression, we get 1 minus cosine of 0 over 0 plus 0. Well, cosine of 0 is 1. 1 minus 1 is 0. And so we get another indeterminate form, 0 over 0. So in both of these examples, we are primed to use L'Hopital's rule. Let's see how that'll work. So here in our first example, we will apply L'Hopital's rule by differentiating the numerator and the denominator. Both of these derivatives are very straightforward. As in the numerator, we know that differentiating e to the x is very simple. It just gives us e to the x back. And in the denominator, we just have to do a little bit of the power rule, giving us 10x minus 3. Just as before, we will plug in infinity and see what happens. Well, the numerator is still infinity, and the denominator, being a linear function, still gives us infinity. Since after one application of L'Hopital's rule, we got another indeterminate form, we will apply L'Hopital's rule once again. And so applying L'Hopital's rule one more time. And here I'm just adding a little LH over my equal sign, just to remind myself that I am applying L'Hopital's rule at each of these steps, so I have taken a derivative. We get that the numerator is still e to the x, that has not changed, but my denominator now, the derivative of 10x minus 3, is simply 10. This now gives us infinity over 10, or simply infinity. Since we got an infinity for our answer and not an infinity divided by infinity, we can stop here and we can conclude that this limit equals infinity. In other words, the original function will grow without bound. So here we continue to apply L'Hopital's rule until we got either a real number or plus or minus infinity. Let's see what'll happen in part B. So in part B, we have the limit as x goes to 0 of 1 minus cosine of x over 3x squared plus 7x. And we can see that if we plug 0 in, we get 1 minus 1 over 0, or again, 0 over 0. So we will proceed by applying L'Hopital's rule, taking a derivative of the top and the bottom. In the top, we get simply sine of x. And in the denominator, we get 6x plus 7. Attempting to evaluate this limit by direct substitution. We get sine of 0 in the numerator, or 0, and we get 7 in the denominator. Well, 0 over 7 is 0, a real number, so we can stop at this point and conclude that this limit equals 0. Note that we would not want to continue taking L'Hopital's rule. If we continue to take L'Hopital's rule, we would get a different value. We would get 1/6 if we applied L'Hopital's rule once again. That is a mistake because it doesn't make sense to apply L'Hopital's rule again, because this limit that we are looking at here is not in indeterminate form after one application of L'Hopital's rule. So remember, every time you apply L'Hopital's rule, you need to check to see, does that new limit exist or equals infinity? If it does, great, you're done, stop. However, like we saw in the first example, if you get an indeterminate form after one application of L'Hopital's rule, continue to apply L'Hopital's rule until you do not get an indeterminate form.